Hello, my name is Shanakovsky, and this is my Lab 5 Choose Your Own Adventure. In this lab, I observed the motion of a tennis ball oscillating in a pendulum on a stretchy string, which was similar to spring, using Tracker. I created a computational model using Newton's second law and the energy principle, also known as the first law of thermodynamics, in GlowScript v Python to predict the motion of the tennis ball and compared this with the observed motion. I graphed the position of the observed and modeled balls over time and graphed the change in kinetic energy, gravitational potential energy, spring potential energy, and total energy over time. The inspiration for this lab was the game Tetherball, where a ball is attached to the top of a pole with a string and players hit the ball to each other. I wanted to model the motion and to figure out the energy of the ball when it is swinging back and forth freely in Tetherball. Some fundamental physics principles of this lab were first that I observed the interactions of a spring mass system with the surroundings because the string acted pretty similar to a spring. The net force on the mass is the force of gravity, and the force of the spring also, I had to use Newton's second law to calculate the position update formula and the velocity update formula with a very small delta t and iteration in GlowScript to create a computational model of the mass's motion. I also had to use the energy principle, where delta E equals W plus Q, which equals delta K plus delta UG plus delta US to calculate all of those different energies. When I took the video, I found that the total time, I also used a very small delta t. I found the ball mass, the ball initial position, the initial velocity, which was 0 because the mass started at rest, and the periods, where the x period was actually bigger than the y period, the spring constant, and L naught, and I created a CSV file of the x and y positions of the observed motion of the mass. Also, as you could see in this video, you see the ball moving in a pendulum, and it shows the graph and for the x direction over time and a table of the x and y directions over time. In the coding, I updated the net force with the force of gravity and the force of the spring. I also updated the ball velocity formula and the ball position update formula to match the ones derived from Newton's second law. I updated the kinetic, gravitational potential, spring potential, and total energies and the changes in these energies in the code using this energy principle. I also, as I mentioned before, calculated and updated the spring constant and L naught using these formulas to make sure that all of the numbers in the code match what would be calculated in reality so the model would be accurate. I also created two different codes with the same initial data to graph the y position over time on one and the x position over time on the other because the ball oscillated in both the y and x directions. And both the codes looked like these listed below, except in the x position code, I had a graph of ball.pos.x instead of ball.pos.y because it was graphing the x position over time. And here is just what the codes look like when you run them for the X position and for the Y position. And as you can see in both, it graphs the change in energy over time and also the changes in position over time. And you can see that the period for the Y position is shorter than the period for the X position. And also there's differences in their amplitudes. So the observed motion and model motion of the tennis ball have the same period in the x direction and also the same period in the y direction, but the modeled motion has a greater amplitude than the observed motion. This could have been due to F net for the observations not equaling Fg plus Fs because of drag force or other dissipative forces from the surroundings. Also, this could have been due to the stretchy string having a mass and observed motion, while the modeled motion does not take this into account. And the GlowScript computational model could be improved in the future by adding a drag force to FNet to make the predicted motion more realistic. Once again, you can see in this graphs on the bottom, especially in the Y position over time, that the amplitude of the observed motion of the mass is smaller than the amplitude of the modeled motion of the mass. Is the energy principle satisfied? Yes. Delta E is always 0 and constant because delta E equals delta K plus delta UG plus delta US, and the kinetic, gravitational potential, and spring potential energies also always cancel each other out. This results in no energy transferring between the spring mass system and surroundings, but there is an energy transfer within the system between the string and the mass, and you can see this in the graph below because always delta E, which is the orange line, is 0. However, the periods for x and y are different. We can see that the period for x is about twice as much as the period for y, and because the y position's period is half the period of the x position, it will complete 2 oscillations in the same amount of time that the x position will complete 1, and you can see that on these graphs on this side, where the y position completes 4 oscillations, while the x position only completes 2 oscillations. And that is all. Thank you.